Hey guys, so in this video we're going to practice some problems involving the equilibrium constant Kc. So we've discussed that the equilibrium constant can be expressed in terms of concentration, Kc, and pressure, Kp. Now in order to solve for the equilibrium constant, the equilibrium concentrations or partial pressures of all the products and reactants must be known. But conversely, if a chemist wants to know the equilibrium concentration of a certain reaction component, they can solve for this information if the value of the equilibrium constant is known in addition to the equilibrium concentrations of the other reaction components. So let's try an example problem for each scenario. Now in some situations you may know all of the equilibrium concentrations in the mixture except for one of the reactants or products, and you will be given the equilibrium constant for that reaction at a certain temperature. So for example, we have the above equilibrium mixture and we're given the concentration of COF2 to be 0.255 molarity and the concentration of CF4 to be 0.118 molarity, and we're asked to find the equilibrium concentration of CO2. So we're asked to find what is this concentration of CO2 at equilibrium, and we're given the Kc value. So we can set up our law of mass action equation of products over reactants raised to the respective coefficients. We're going to have products, our CO2, which is what we're solving for, that concentration, raised to its coefficient, which is a 1, so we don't need to show that because anything raised to the first power is just itself, times the concentration of CF4 raised again to the first power over the concentration of COF2 squared. So plugging in the information we know that the Kc value for this reaction temperature, which happens to be 1000 degrees Celsius, is 2.00. Now that's going to be equal to the concentration of CO2, which is what we're trying to figure out, that equilibrium concentration, times the concentration of CF4, which is given to us as 0.118 molarity, over the concentration of COF2, which is 0.255 molarity, squared. So we can solve for the CO2 concentration at equilibrium by simple algebra. If we square this 0.255 value and multiply by it on both sides in order to cancel it out from the denominator, we get that 0.130 is equal to 0.118 molarity times this concentration of CO2 at equilibrium, which we're trying to solve for. Now in order to isolate for the concentration of CO2, we can divide by 0.118 molarity on both sides, and this is going to give us our equilibrium concentration of CO2 is equal to 1.10 molarity. Now in other scenarios, you may only be given the equilibrium concentration of one reactant or product, but be responsible for determining the equilibrium constant. So in order to determine the equilibrium constant, you need to first calculate the equilibrium concentrations of the other reaction components using an ICE chart. So the abbreviation ICE actually stands for Initial Change in Equilibrium Concentrations. So in this type of problem, a chemist may know the initial reactant concentrations in the mixture and be able to measure the equilibrium concentration of a reaction component through some experimental method, usually a spectroscopic method. So take the following problem for example. The reaction mixture below initially contains a 0.087 molar concentration of CH4. At equilibrium, the concentration of H2 is 0.012. Find the equilibrium constant. So in order to find the equilibrium constant, we need to know the equilibrium concentrations of all the components in the reaction mixture. Now in this case, we only know the equilibrium concentration of H2 is 0.012 molar. And we know the initial concentration of CH4 is 0.087. So we're going to utilize our ICE chart in order to calculate the equilibrium concentrations of all the components in the reaction mixture. Now we also know the initial concentrations of CH2 and H2 because these are our products in our reaction. So initially, before the reaction has began, those concentrations are going to be 0 unless otherwise stated in the problem. So an ice chart is a way that helps us organize the information we're given in order to really calculate the change in the concentration that occurs from the initial reactant mixture concentrations to the equilibrium concentrations, which we ultimately need to solve for the equilibrium constant. So this change we designate with some factor of x. Now for our reactants, since we're going to be forming products from the reactants, we're going to be losing reactants, so we're going to be subtracting some factor of x. And this factor is dependent on the coefficient in the balanced equation in front of the respective reactant. So in this case, we're going to be subtracting 2x from the initial reactant concentration of CH4. For our products, we're going to be forming products, so we're going to be adding some factor of x. For C2H2, it has a coefficient of 1, so it's technically adding 1x here. And for H2, we have a coefficient of 3, so we're going to be adding 3x. So now we have an expression that designates the equilibrium concentration of all the components in the reaction mixture. We know that at equilibrium, the concentration of CH4 is 0.087 minus 2x. The concentration of C2H2 is 0 plus x, which is just going to be x. And the concentration of H2 is going to be 0 plus 3x, so that's just 3x. However, we are actually already given that equilibrium concentration of H2 is equal to 0.012. So now we have a way that we can actually solve for this x value, and therefore we can solve for all of the equilibrium concentrations in the reaction mixture. If we set 0.012 molarity equal to 3x and divide by 3 on both sides, we get that x is equal to 0.004. So that means that our equilibrium concentration of C2H2 is 0.004, and our equilibrium concentration of CH4 is going to be 0.087 minus 2 times this 0.004 value, which gives us a concentration of 0.079 at equilibrium. So now that we know these equilibrium concentrations, we can plug them into the law of mass action for the reaction. So our Kc value is going to be equal to the concentration of C2H2, which we solved to be 0.004 molarity, times the concentration of H2, which was given to us as 0.012 molarity, over the concentration of CH4 squared, so 0.079 molarity squared. Now simply plugging this into our calculator, we get that the value of Kc is equal to 0.008. So overall in this video, we learned how to solve for the value of the equilibrium constant from the equilibrium concentrations. Additionally, we learned how to solve for an equilibrium concentration from the equilibrium constant. However, in some situations, none of the equilibrium concentrations of the components in a reaction mixture are actually known. So in the next video, we're going to discuss how to solve for equilibrium concentrations using an ice chart when only initial reactant concentrations are known by the experimenter.